Welcome back. Today we'll study about the force on a current carrying wire placed in a magnetic field. In other words, we can say force on a current carrying conductor in a magnetic field. For this activity, we'll need copper wire, electric shell, horseshoe magnet, connecting wire, stand, once again upper end with the battery and the lower end with the switch key, and the key is connected with the other part of the battery, and the switch must be off. And take a horseshoe magnet and place it. And here, when you observe, we don't see any movement in the wire. Whenever the current is not flowing, the wire becomes straight. Okay, now we'll just observe when the current is passed through. On the current end, you can see that the wire is moving when the current passes through the wire. When the current is on, then the wire moves away, and we can mark S, A, and C. When you off, it come back there. It come back straight again. Now we'll change the direction of the battery. That means the current flowing through it, and on the key again. Nothing happened, as you observe here. Nothing happened to the wire. Off again, and after that, when you put the horseshoe magnet, then the current is moving. Sorry, the wire is moving. From there, what you can observe is that the wire is moving in other direction when you change the position of the current. And we can mark as B. You can see that the movement of the wire when the magnet is there. On reversing the current, the flow of current, the movement of the wire is changed. You can compare these two by looking at these two experiments. Direction of the current changes due to direction of magnetic field. When the current is reversed, then the direction of the magnetic field is changed. When the direction of the current is reversed, then the force is changed. The force is reversed. When the current is flowing downside, then direction of magnetic field is changed. When the direction of the current is from top to bottom, then the direction of magnetic field is changing. It follows the left hand rule, Fleming left hand rule. When the direction is reversed, then the direction of magnetic field also it changes. From this, what can we observe here? The direction of current, it reflects the direction of magnetic field. Let's observe one more. Watch carefully here. When the current is passed through, then you can see that a wire, it experiences the force. It is due to the magnetic induction. Once again, you observe this carefully. When the current is passed through, it's moving here. Once again, let's revise. Observe carefully here. The arrangement here, the conductor is placed between the horseshoe magnet. The battery and the plug key are connected here. The magnet is arranged in such a way that north pole and south pole are vertical. when the current is passed through the current, then the rod get displaced here. The displacement of the rod suggests that magnetic field is produced in the rod because of the electric current. When we know that the conductor is moving towards left. Now we'll reverse the battery. By reversing the current battery, the current will get reversed, and we'll observe what happened here. From here, by reversing the direction of the current, that is the battery, then the magnetic force can be reversed. Now we'll add more battery, and what will happen to the display to the magnetic field? When we add more battery, then the deflection is more, as you can see here. When we add more battery, then it move, the displacement is more. That shows that current and force are mutually perpendicular to each other. From this, what did you observe? We observed that the direction of the current and the force are mutually perpendicular to each other. This can be explained by Fleming left-hand rule. In Fleming left-hand rule, the forefinger represents magnetic field, that is field, and the thumb represents the force, and the middle finger is the current. This is the principle of working of this electric motor, which we will study in the next class. Please stay tuned. Thank you.